So the first series I want to show you is the harmonic series, okay? Okay, so the harmonic series is very simple. It's this specific series, this one here. N equals 1 to infinity of 1 over n. This is called the harmonic series. Okay, to break. Okay, so what is this equal to? Well, if you plug in 1, you get 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus and so on until infinity. Okay, so this series, this specific series diverges. Okay, so that's the first thing. If, and we're going to use it a lot. Okay, you're going to see when we're going to do comparisons, we're going to often compare it to this one because this one diverges. Okay, and I have to show you why it diverges. Okay, but this specific one diverges. So why does it diverge? So proof. Okay, well, this sum here, you can't see. Second. Okay. This sum, so is equal, like we said, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7. I'm going to keep going a bit. Okay. 9 plus 1 over 10 plus 1 over 11 plus 1 over 12 plus 1 over 13 plus 1 over 14 plus 1 over 15 plus 1 over 16 plus 1 over 17 plus dot dot dot. Okay, that's my series. Okay, and what I'm going to do now to show that it diverges is I'm going to, let me think. I'm going to group these two. Then I'm going to group these 4. And then I'm going to group these 8. Okay. And I could keep grouping forever like this. Okay. 2, 4, 8, 16. The next 16, I could group them as well. And I'm going to write like this. 1 plus 1/2. Okay. And plus, if instead of writing a third here, if I wrote a quarter, okay, and so obviously I'm replacing 1/3 with 1/4, which is of course smaller. Okay, so I'm replacing 1/3 with 1/4. Okay, same here. I'm going to replace 1 over 5. I'm going to replace it with 1 over 8. Okay, 1 over 6 with 1 over 8. 1 over 7 with 1 over 8. Plus. I'm going to explain you why I'm doing this. Okay. Plus, and here I will replace all these guys by 1 over 16. Okay, so 1 over 16, 1 over 16, 1 over 16, 1 over 16, and then plus 1 over 16. Plus, and so on. Okay, the next one I will replace by 1 over 32, but forget for now. Okay, so what did I just do here? Okay, I replaced 1/3 by a quarter, which is smaller. 1/5 I replaced by 1/8, which is smaller, smaller, smaller. Okay, so I'm just replacing a bunch of terms by smaller terms. Okay, same here. 1 over 16 is less than 1 over 9. Okay, so for sure, the new series that I'm writing is smaller than the other one. Are you okay with this? Would you like me to repeat what I just said? Okay. Right? I'm assuming you have no questions. That means you understand. Okay. What's the point of doing this? Because now, what is this series equal to? Okay, I'm writing equals. This here is equal to, so it's 1 plus 1/2 plus, well, a quarter plus a quarter, that's 2 quarters, that's 1/2. 1/8 plus 1/8 plus 1/8 plus 1/8, that's 4/8, that's 1/2 again. Plus 1/16 8 times, that's 1/2 again. Plus, and I keep going like this, and I end up with an infinite amount of halves. Okay, so if I do 1/2 times infinity, I'm going to get infinity. Okay, and so I'm getting infinity. And therefore, I just showed that the sum of the harmonic series, sum of 1 until infinity of 1 over n, is greater than or equal to infinity, so it has to diverge. You understand? It's definitely, there's no number that I cannot reach with this series. If you want to, if you're telling me, will this sum, this infinite sum, eventually reach 10 million, I'm going to tell you yes, it will. After a very long time, after billions of terms, you will exceed 1 million, the sum. And I chose 1 million. It could be 10 to the power of 10 million. Any number. You will eventually surpass that. Okay? Any questions?
Sir, can you repeat the last part? Like, how did you determine that it's infinity?
Okay? Because this is 1/2 plus 1/2 plus 1/2 plus 1/2 infinitely many times. Do you understand that?
Yes.
Okay, so this is like, if you want, I'm exaggerating the way I'm writing, it's 1 plus 1/2 infinitely times, infinitely many times. So 1 plus 1/2 times infinity is infinity, right? The half times infinity is infinity, plus 1 is still infinity.
Okay, thank you.
Okay. Any questions?
Sir, I'm a bit confused.
Yes?
Like we did 1 plus 1/2, then we replaced like one. Why did we replace? Like why did we take the two terms starting from 1/3 and not like from 1/2?
I'm sorry, why did?
Why did we like um change the 1/3 to 1/4 instead of taking in brackets like 1/2 and 1/3 and 1/4 till 1/7?
You could. You're free to do whatever you want. It's just that this is convenient for me. This is a way for me to prove that I have 1/2 plus 1/2 plus 1/2. If you combine 1/2 plus a third, I don't know what if you'll get something as nice as this. Maybe,
Okay.
but that's not the only way. There's other proofs.
Okay, perfect. Thank
Okay,
you.
no problem. So the second type of series that we need to recognize is the what we call the P series. Okay, so what's a P series? So a P series is a series right here of the form So this is a P series sum, n equals 1 to infinity, 1 over n to the power of p. That's a P series. So 1 over n to the power of a number. Okay, so they're very easy to recognize. And how do you determine whether this series converges or diverges? Well, it depends on the value of p. Okay, so two possibilities. So if p is less than 1, okay, then the series, the p series, diverges. And if p is greater than 1, yes, that's pretty easy. N equals 1 to infinity, the p series converges. Okay, that's like this. Okay, any questions? I'm expecting one question. Okay. So
Sir,
one, yes.
what happens if P is negative?
Okay, so if p is negative, it means that it's going to be n power, it's going to be n power positive number, so it's for sure going to diverge. You understand?
Okay.
1 over n to the minus 2 is the same thing as n2. If you add n2, so it's 1 squared plus 2 squared plus 3 squared, of course it's going to diverge. Okay, so obviously we're talking about positive p's. Okay, okay, so it's still a good question, but what happens at p equals 1? I wrote less than 1, I wrote bigger than 1. What happens if it's equal to 1? Is it diverge or converge?
Then it's a
It's like
harmonic.
Oh, very nice. Who said that? Very nice.
Aaron?
Yeah, very good. If p is equal to 1, exactly. If p is equal to 1, then it's a harmonic. And if it's harmonic, it converges or diverge?
It diverges.
It diverges. So the or equal, I'm going to put it here. Okay, so if p is less than 1 or equal to 1, it diverges. Very good. Exactly. If it's equal to 1, it becomes the harmonic series with diverges. Excellent. Okay. So let's do a few examples of this. So that's very easy. Okay, so we already have two series that we can recognize, the harmonic and the p series. Okay, so let's do a few examples. So does the following series converge or diverge? Okay, so first one, sum and 1 to infinity, 1 over n cubed. Second, okay, so it's pretty easy. N equals 1 to infinity, 1 over cubic root of n4. 3, sum n goes from 1 to infinity, n over square root of n5. and for some cubic root of n. Okay, so tell me if it converges or diverges, each of them. Okay, so the first one converges because, of course, p is greater than 1. So it converges. Second one, converge or diverge?
Converge.
Converges because p is 4/3, right? 4/3, which is bigger than 1. Converges. This one here, so here we have to do a bit of work. Sum n equals 1 to infinity. So if I simplify n over, this is n power 5/2. So it will be n over 1 over n to the 3/2. So again, greater than 1, so it converges. And this one, converge or diverge?
Diverge.
Diverges, perfect. Okay.
Sir, could you please explain number 3?
You understand how we got this or no?
Yeah,
Oh, this you get?
yeah.
So that's it. So p is
Sorry,
3/2.
I don't get how you got to, yeah.
Oh,
how
you don't get, I got this.
3/2.
Okay, no problem. So n over the square root of n5 is equal to n over n power 5/2, right? Square root of n5 is 5/2. And then if you minus the exponents, right, or you divide by n and by n top and bottom, you will get 1 over n to the 3/2.
Okay, it's good. Sorry, I thought it was 6. Thank you.
Oh, okay, no problem.
Sir,
Yeah,
are these series only true if n equals 1?
if it starts at 1, you mean?
Yeah, if it starts at 1.
No, you can start anywhere. Doesn't matter. Okay. So tests for determining whether a series converges or diverges. Okay, so that's pretty much what we're going to be doing for a while now. There's, I think, about seven or eight tests. Okay, these are tools that I'm giving you to use once you see a series to determine and do sort of a diagnostic of your series. Is it going to converge, diverge? Test 1, test 2. Let's see. No, this doesn't work. Next test. That's what you're going to do. Okay, I'm going to try to give you a flow chart on which test to use. If yes, do this. If no, do this, and so on. Okay. The first test is called the divergence test. It's the easiest one. Okay, which is also called the nth term. I think it's called the nth term test. In some books, you'll see it like this. Okay, and it says as follows. If the limit as n approaches infinity of an is not 0, then the series diverges. Okay, so this is the first thing you should always do. When you get a series, you take the term inside the series and you find its limit as n approaches infinity. 99% of the time, this limit here will give you 0. But if it ever doesn't give you 0, you could stop your problem right away. You could say that your series diverges. You're done. Okay, so it's almost never going to happen because that's too easy. Okay, so for example, the series n1 to infinity, let's say n squared plus 5 over 2n squared plus 1. Okay, so here's a series. Does it converge or diverge? Well, you're going to take the term inside. Okay, so you're going to take limit as n approaches infinity of n2 plus 5 over 2n2 plus 1. That's infinity over infinity. How do you evaluate this limit? You could use L'Hopital's rule. Okay, just like you did in calculus 1. And that's 2n over 4n. And that gives you 1/2, which is not 0. It's not 0. Therefore, the series diverges. Okay, and then you have to specify, how do you know that it diverges? You have to specify the test that you used, okay, by the divergence test. Any questions? Okay, so this is the first test, very, very easy. Let me give you another example. Sum n equals 1 to infinity, so n over n2 plus 1. So we want to apply the divergence test here again. So what do? I'm going to take the limit of the term. Okay, so let's do this. Limit as n approaches infinity of n over n2 plus 1. Infinity over infinity, we use L'Hopital's rule if you want. Limit n approaches infinity, derivative of the top is 1 over 2n, and that gives me 1 over infinity, which is 0. What does that mean?
It converges.
Converges.
Did I say that it converges? Nope. Did I say if it's equal to 0, it converges? Nope. I said that if it's not 0, it diverges. If it's equal to 0, I don't know. It could still converge or diverge, I don't know. By the way, this one diverges. Okay, but I don't know. The only thing I know is that the test, okay, or the divergence test actually, okay, the divergence test fails. Okay, it means that I have to now go to another test. Okay, so I tried to get the answer right away, it failed. No, it's not that easy. Okay, here it was that easy. It was not 0, it diverges. Here it's equal to 0, test fails. Let's move on to another test. Okay, so I'm going to write this warning here because that's a mistake that I see. Okay, and just remember this, so be very careful. Warning, okay, if the limit as n approaches infinity of an equal to 0, that doesn't mean, okay, forget the if. Okay, so this limit equal to 0 doesn't mean that the series converges. Okay, it's not true. Okay, the best example is the harmonic series, right? The harmonic series, the limit n approaches infinity of the term is 1 over n, of 1 over n is still 0, but it's 0, but it still diverges. We proved it before. Okay, I hope that's clear.